In group theory, the first isomorphism theorem is a masterpiece. The kernel of a homomorphism from a group G being a normal subgroup, and any two elements of G differing by a member of the kernel corresponding to the same element, allows us to construct a well-defined isomorphism between G quotiented by the kernel and the image of the homomorphism. It's ubiquitous in abstract algebra, allowing us to prove results such as the rank nullity theorem in linear algebra. With respect to the third isomorphism theorem, even if one doesn't have much algebra knowledge, provided our notation is sufficiently nice, one could be convinced that this is a sound result, looking like how fractions behave. But the second isomorphism theorem, what the hell is even that? It's the ugly duckling of the three isomorphism theorems. This doesn't convey any useful information to me at first glance. I also distinctly remember having a conversation with my group theory supervisor in university about this capital letter N right here, how redundant it feels. Every coset of Hn quotiented by n can be reduced from being written as little h little n times n to little h times n. But yet we can't get rid of this big N on the numerator because n isn't necessarily a subgroup of h, whence the notation h quotiented by n would be ill-defined. So what's actually going on here? This is an example of when minimal notation is not always simple. We can expand the numerator on the left-hand side back out into G intersect h, obviously because h is contained in G. So on the left we have a quotient of intersections by h, aka restrictions by h. Let's make it a bit more vertical. On the right hand side we have what seems to be the quotient group G quotiented by n, but only cosets representable by an element of h. Whilst Hn quotiented by n may be a computationally efficient way of writing this, and Hn satisfies the correspondence theorem, which we'll come back to way later, it's really ugly, and so just for the purpose of this video I might propose some non-standard alternative notation, like this, inspired by restricted characters from representation theory, an extension of group theory. Perhaps the tipped arrow is unnecessary, but I like it. So on the right hand side of the isomorphism we have the restriction by h of a quotient group. I'll put them all together up at the top. So the second isomorphism theorem is telling us that we can restrict and then quotient, or quotient then restrict, and up to isomorphism we have the same thing. To me, the second isomorphism theorem is about two things. Firstly, restricting by a subgroup of G and quotienting by n commute via this isomorphism. And therefore secondly, to understand the structure of a quotient group G quotiented by n restricted by h, look at the structure of the quotient group of G and n each restricted by h. That way we have h on the numerator of the quotient notation. You know what I mean by numerator, it's not exactly a fraction, but you know what I mean. And thus combining both together, it seems to almost be a law of distributivity. Like how multiplication is distributive over addition because a times b plus c is a times b plus a times c. It's the distributivity of restriction over quotienting, whereby restriction on the left-hand side is intersection by h of g and n, and on the right-hand side restriction is reducing the set of elements that we allow to span the coset space of G quotiented by n from G to h. This restricted coset space may or may not be equal to the whole coset space, as we will soon see. Let's see a couple of examples and then prove the second isomorphism theorem. We're going to take G to be the integers z, and h to be multiples of 6, and n to be multiples of 10. I've chosen the numbers 6 and 10 so that they have a factor in common, i.e. they're not coprime, so that Hn, the combinations of additions, isn't the entire group G. We can easily compute that Hn is multiples of 2, the greatest common divisor of 6 and 10, which could be obtained by prime factorization or the Euclidean algorithm, and h intersected with n is multiples of 30, the lowest common multiple of 6 and 10. Hn quotiented by n is the even integers quotiented by multiples of 10, and h quotiented by h intersect n is multiples of 6 quotiented by multiples of 30. As we said earlier, even if one didn't have too much algebra knowledge, this result now is at least notationally plausible, looking like fractions. Notice that we didn't end up with the same group on both sides of the isomorphism either, but two different groups that are isomorphic. Let's take a second important example. Let g be the integers, h be multiples of 6, and n be multiples of 7. 6, 7, I know. Hn is equal to the whole integers z, since 6 and 7 are coprime, and the extended Euclidean algorithm gives us a linear combination of 6 and 7 equal to the greatest common divisor, 1. And h intersected with n is multiples of 42. Hn quotiented by h intersect n gives us 6z quotiented by 42z, which may look at first glance interesting. It's different from g quotiented by n, but on the right hand side, g quotiented by n, restricted to h, is the integers quotiented by 7z, which is our original g quotiented by our original n. Our restriction of the quotient group to cosets generated by h ended up being the same as our original coset space of g quotiented by n. This is why I've been a bit careful in this video and tried to say restriction by and not restriction to whenever I can, lest I imply speciously that restriction by a proper subgroup of G would lead to a proper subgroup with the quotient group. Just because we have a proper subgroup H of G doesn't mean that G quotiented by N restricted to H is going to be a proper subgroup of G quotiented by N, because H and N combined together may generate the entirety of G. This may be intuitive here with groups based around arithmetic like the integers, but when deep in abstract algebra, dealing with abstract groups like dihedral groups and alternating groups, it's a good pitfall to remember to avoid. Okay, so we played around with the second isomorphism theorem now, so let's prove it. We're going to do so by applying the first isomorphism theorem to the canonical quotient map Q from G to the coset space of G quotiented by N. This map is a homomorphism by virtue of n being normal, which is a crux of the role that normal subgroups play in being able to form well-defined quotient groups. If we were to apply the first isomorphism theorem straight away to Q, the kernel of Q is the elements of G that get mapped to the identity coset n. Hence the kernel is n itself, and the quotient map is certainly surjective, whence the image of Q is the entirety of G quotiented by n. So applying to the first isomorphism theorem, we end up with G quotiented by n is isomorphic to G quotiented by n. Okay, big wow, just a bit of a sanity check, but now let's progress. What if we restricted Q from mapping from G to mapping from H? The kernel of this homomorphism is the elements of H that get mapped to the identity coset in G quotiented by n. For Q mapping from G, this was exactly all of n, which we could trivially expand to be written as G intersected with n, since n is contained in G. Similarly, the kernel of Q restricted to H is H intersected with n, which we can't simplify by unexpanding, since n isn't necessarily contained in H, so this is the simplest way of writing the kernel. The image of Q mapping from G was certainly the entire collection of cosets, i.e. restriction by G does nothing. But Q restricted to mapping from H is only all cosets expressible as little h times n, i.e. G quotiented by n restricted to H. And so, applying the first isomorphism theorem, we have our result. The reason we end up with two different groups on the left and right hand sides of the isomorphism in general is because the actor quotienting seems to lock in our denominator. On the right hand side, this is n, and our further restrictions of the cosets to be representable by elements of h doesn't change the denominator, doesn't change n. Whereas the kernel of the quotient map Q restricted to h takes a new form as n intersected with h. The only time these groups would be equal is if the denominators are equal, that is, h intersect n is n, i.e. if and only if n is contained in h, i.e. n is a normal subgroup of h. In that case, both sides are h quotiented by n. The only thing to really do now is to show an explicit form of writing g quotiented by n restricted to h, that it can be given in the form of the final term of this equation, as hn quotiented by n. As I hinted at earlier, the way to do this is to use the correspondence theorem. That is, that any subgroup J of the quotient group G quotiented by n can be written in the form K quotiented by n, where K is a subgroup of G containing n. The way to establish this is to let K be the union of all of the cosets in J. This will be closed by definition of the group operation in a quotient group being that the resulting coset of combining two cosets together with representatives G1n and G2n is the coset containing G1, G2n, which is well defined because n is normal. And we find that K is given as Hn, therefore. Sometimes with quotient groups we want to just talk about the cosets themselves. Other times we wish to talk about the elements of the cosets under composition with each other. We can play around with the group Hn on its own manually to get a feel for it if we wish. If we combine together H1N1 and H2N2 as H1N1, H2N2, at first it looks like we might run into a problem. That is, we can't write it in the form of a single H3 composed with a single N3. But actually we can. Since the group N is normal in G, H2 inverse N1 H2 belongs to N. Call it N1 prime. Thus N1 H2 equals H2 N1 prime, and so we can regroup our H's together by passing them leftwards through the N's at the expense of mutating the N's. Thus our resulting element is of the form we want. If we wish to disregard the N's entirely, agnostic of how mutated they become, we can quotient out by n to get a group that almost looks like H. There's two reasons why this isn't simply H on its own, though. Let's go through one of our examples from earlier to see why. Firstly, not every coset representative of n's coset space over H can be written as a little h times n. For example, the number 2 belongs to Hn, but neither h nor n individually. It's just part of the Cartesian product. But it is just as valid a coset representative of the coset 12 as number 12 is, which does belong to H. Secondly, pure elements of H that differ by an element of n are the same thing in this group. For example, 18 and 48 belong to H, and they're different in H, and thus in Hn, but quotienting by n they are the same, differing by 30, an element of n, a multiple of 10. So whilst any coset of Hn quotiented by n will have at least some representatives purely in H, not all of these pure H elements give rise to different cosets. Precisely, those elements of H that differ by a member of n are the same in this group. Thus, this group is like H modulo H intersect n, and lo and behold, we have rediscovered that the structure of this group is H quotiented by H intersect n, the left-hand side of the second isomorphism theorem. So we've proven our result twice really, this time from right to left, which makes for a good place to stop. So there we have it. I hope this was useful since the second isomorphism theorem is pretty opaque at first glance. The takeaway, the mashma'ut, the logos of the second isomorphism theorem is that if one wishes to understand the structure of a quotient group G quotiented by n restricted to H, a subgroup of G, look at the structure of the quotient group of G and n each restricted by H. I'm entering this video into 3 Blue 1 Brown's Summer of Mathematics expedition, and the link is in the bio, and make sure to like, comment and subscribe if you enjoyed.